Sir, just 2 minutes, sir.
Okay.
The participants will crash under now will start, sir.
Okay. Sure.
Please. Sir. Sir, Sir, check this, sir.
Yes, sir.
Sir, officially it starts.
Shall I start?
Sir, officially I will start
Yeah.
with the welcome. Okay, sir. So, good afternoon, everyone present here on the 6 days International Faculty Development Program on Futuristic Research in Mechanical Engineering. On behalf of SRM University, Amapuram campus, Faculty of Engineering and Technology. I'm happy to welcome you all. First of all, I want to welcome our respected chairman, sir, co-chairman, sir, and our honorable chief director, director, sir, and our beloved deans and commissioner, sir, and our vice principal academic as well head of the department, Dr. G. Prabhakaran, sir, all other heads of the departments, and faculty members from various departments. More especially, each one of these today's participants, welcome you all. And my special welcome to Dr. N. Alagappan, sir. So he is going to present today's session. So I welcome you, sir.
Yes, sir.
I request one of the coordinator, Krishna, for giving introduction about our chief guest.
Thank you, sir. Thank you, Dr. Navi, sir. Thank you, sir. It is my pleasure to give an introduction about our chief guest, Dr. Mech, Assistant Professor, Department of Mechanical Engineering, Annavar University. Sir has completed his PhD at Annavar University and highly placed professional 14 years of experience teaching. Sir has been awarded by Thinking International Research Foundation as Excellence Teaching in Higher Education. And Sir owns more than 30 papers in reputed journal and is lifetime member of various associations like International Association of Educators and Researchers, International Association of Engineers, and Indian Association for Technical Education. And he is acting as a editorial board member for various journals. Sir has conducted many short-term courses for school students and diploma students sponsored by AACD for the project. being an active inspiration. It's nice to have you with us today. Thank you. The stage is yours. Thank you.
Sir, the session is yours, sir. Please start.
Yeah, thank you very much for the nice introductions. And also thanks for the management of SRM Institute of Science and Technology for giving the chance to be present here. And today's topic is nanofluids in wickless heat pipe thermosiphon. Next slide, sir. Sir, next slide. Yeah, nanofluids in wickless heat pipe, which is also known as thermosiphon. Wickless heat pipe, which is also known as thermosiphon, since it is a gravity assisted, that's why it is called as thermosiphon. What we are going to discuss in this session, how we can apply the nanofluids in thermosiphon. So that is a major idea of this presentation. Next slide, sir. So first I start with nanomaterial, which is commonly defined as a material with an average grain size of 100 nanometer, which is equals to 1 billion nanometer, which is equals to 1 meter. So why we going for nano? So that is our next slide. So next slide, sir. Why nanofluids? Because according to the literature survey, we have gone through the survey of literature. Based on that, the microfluids are used previously. So due to that, microfluids in a micro channels, it is clog off. There are a lot of cloggings are happened in micro channels. That's why the researchers can develop another kind of fluid, which is known as nanofluid from the nanomaterials. So each day advances in nanotechnology, enabling data and information revolution. There is a lot of research or progress in nanofluids still in nowadays also. The new developments based on nanofluids are in solar energy, heat exchanger design. One of those that is thermosiphon, heat exchanger. It comes under heat exchanger. Cancer therapy, safer surgery, and now also it is used in cosmetics. Then to develop better oil and lubricants. So next slide. Next slide, sir. So this is a diagram which explains large scale to nano scale. For that, first the football, which is 22 centimeter, and a flea, which is known as insect, 1 mm, and red blood cell, which is micrometer, 7 micrometer, and virus. Recently, we have faced coronavirus. So coronavirus size is 40 to 140 nanometer. So we know the effect of corona. So that the virus is starting from nanometer scale, and buckyball, which is wired structure of circle, that is also 0.8 nanometer, and sunscreen recently TiO2, which is developed, that is 35 nanometer size. So next slide, sir. Sir, next slide. Sir, next slide. The next slide.
Yes, sir. Yes, sir. Please, sir. Please. Thank you, sir. Next slide. Go matter. Sir, 1 second, sir, please.
Yeah, okay.
Sir, please continue, sir.
Yeah. Now, classification of nanomaterials. So we are defining nanofluids. Before that, we are going to see what are the nanomaterials available. So nanomaterials are in 1 dimension, 2 dimension, and 3 dimension. 1 dimensional nanomaterials are nanofibers, wires, and rods. And when you're going for 2 dimension, it is in films, plates, and networks. And the films are nowadays used. Nanofilms are nowadays used as solar transparent sheet instead of glass. So the 3 dimension, which is nanomaterials are copper oxide, zinc oxide, titanium oxide, and all these oxides which are present comes under nanomaterial, that is in 3 dimension. So next. Yeah. Next, nanoparticle shapes and types. We are having, there are different shapes and types are available in nanoparticles. So first one is spherical. Usually the spherical types of nanoparticles are carbon-based, graphene, and CNT. CNT means carbon nanotubes. Cubic structure having ceramic-based, cerium oxide, titanium oxide, and aluminum trioxide. Thereafter, crystalline structure-based, metal-based, all the types FeO, CEO, and CEO also there. So platelet, non-metal based, ZNO and ZNS, cylindrical, polymeric based, amorphous, lipid based. Amorphous, which means they're shapeless. So there is amorphous. The next slide. So this is the introduction of nanofluids introduced by Choi and Eastman in the year of 1995. Nanofluid refers to the suspension of nano-sized particles in the base fluid. The base fluid can be aqueous or non-aqueous in nature. It's not a simple solid or liquid solid mixture. It requires special requirements for the preparing the fluid. Next slide, sir. So preparation method for nanofluids. We are having two methods. One is single step method and another one is two-step method. The single step method, production of nanoparticle and dispersion in a base fluid are done simultaneously. And this single step method, which is mostly applicable in agriculture field, because both this happening in a simultaneous of base fluid. So there is only useful for agriculture field, even though it is used in heat transfer field. But the cost of preparing this kind of nanomaterials is a little bit higher when compared to two-step method. So usually heat transfer and all other application sites were use of two-step method, because the materials are first produced, then it is dispersed in the fluid, which means aqueous fluid like DI water. Likewise, all the fluids are dispersed by the materials. So next slide. So this is nanofluid. Base fluid, nanoparticle, which gives nanofluid. Base fluid, which means that which is water, oil, or any kind of chemical fluid in which the nanoparticle is dispersed and it is mixed. Therefore, it is called nanofluid. The special requirement for the nanoparticle is surfactant. Because once you put the particle in a water, it's started to sediment, which means it started to settle down. So while avoiding the settle off, so we are using surfactant. So this is it's not a simple liquid solid mixture. So that's why it is special requirements are needed to prepare the fluids. So this is nanofluid. Next, sir. So surfactants are the compounds. Before that I said special requirements required to prepare the fluid. So that is surfactant. Surfactants are the compounds that lower the surface tension. Once the surface tension of our base fluid is reduced, so that our nanoparticle is properly mixed and gives the nanofluid. So surfactant play an important role in a droplet-based microfluids. So microfluids also use of surfactant for the stabilization of droplets. But here the surfactants is used for stabilize the fluid, which means to stabilize the nanoparticle with the fluid. So that's what surfactant, use of surfactant. Next slide, sir. So this is, I'm taking the example of Fe3O4 nanoparticle, how it is mixed with surfactant. For the Fe3O4 nanoparticle, we will take kerosene and oleic acid as a surfactant along with DI water, which gives Fe3O4 nanofluid. So next slide. So these are the various surfactants which is available in the market. One is fatty acid, oleic acid plus kerosene, ethylene glycol, colosate, then trisodium citrate dihydrate, polyvinyl, citryl trimethyl bromide, trimethyl ammonium hydroxide, Senegal, then sodium decoyl benzoate sulfonate, sodium decoyl sulfate, and sodium sulfate. The next slide. So equipments for preparing nanofluids. So magnetic stirrer, first one, and another one is probe type sonication, and another one is bath type sonication. Magnetic stirrer, which is used only for non-metal nanoparticles, because once it is a metal, it stick on with the stirrer and it may able not to produce the fluid properly. So for that metal type, we are using probe type sonication and bath type sonication. So next slide. So how much amount of volume we have to take for the fluid for the volume fraction? So this is reduction data from the literature. Volume fraction, which is nothing but volume of nanofluid by volume of nanopowder by volume of nanofluid. So this is what volume fraction. So here I am taking 80 milligram per liter of Fe3O4 for the reference and 100 milligram per liter another reference. Next slide, sir. So this is the bath type sonication. This is prepared for my research work. So once I started pour the water in the bath type, afterwards I pour Fe3O4 nanoparticle inside the sonication machine. So afterwards I can set the time for 1 hour. The machine start to produce vibration. So once you check here, vibration is here. So due to the vibration, the particle mixes with the water properly. And after sonication process, that Fe3O4 material with the fluid, around 45 days, it is stabilized. Afterwards, it started to sediment. Similarly, CeO2, it goes up to 75 days. Thereafter, it started to settle off. So there is a major problem in nanofluid. So once it settle off, your heat transfer rate will be changes because of the sediment of the particles inside the heat exchanger material or whatever the application side you are using. So this is a major drawback. In order to avoid that, continuous working of machine will avoid this kind of sediments. So next slide. So nanoparticles influence of nanoparticle, how it will influence by means of shape, size, dispersion, and type. So in this 4 category only where nanoparticle get influenced. Next slide, sir. So challenges, what are the challenges we are facing while using nanofluids? Scale up capacity, that's what I'm saying. It's started to settle off, it produces scale. Then temperature, once it is scaled off, the temperature automatically rises in a particular point. Then surfactant and additives, if you are not selecting the surfactant or additives in a proper manner, then it is again a trouble which is easily settle off immediately. Then corrosive effect, after that nanofluid cost wise, suppose you are choosing a platinum as a nanomaterial, then it cost wise higher. Similarly, gold nanoparticle, diamond nanoparticle. So the cost wise it is higher. Increase in nanofluid viscosity. So all these challenges of nanofluids before you starting your research work. Next slide. So stability evaluation method. There are 3 kinds of method available. So one is sedimentation and centrifugation method, and zeta potential analysis, spectral absorbency analysis. So these are the 3 methods to how your nanofluid is stabilized. So once in the stability method itself, you know that how many days your particle will be stable. So for example, 45 days, 60 days, let's say that before that, so 60 days, you see cerium oxide is stable. That is not by means of zeta potential analysis, we will analyze that. Next slide, sir. So these are the characterization of nanofluids. SEM, scanning electron microscope, TEM, transmission electron microscope, XRD, X-ray diffraction, Fourier infrared transformation, thermogravimetric analysis, zeta potential, energy dispersion sources. Next slide, sir. So flow characteristics, nanofluid can be in both the fluids, Newtonian moment and non-Newtonian moment. Newtonian moment obeys Newton's law of viscosity. Non-Newtonian moment does not follow the Newton's law. So your nanofluid can obey both this. Next, sir. So SEM analysis we have done for Fe3O4 and CeO2. In the SEM analysis, we can know the size of the nanoparticles. We have selected the size from 10 to 15 nanometer, and for cerium oxide, 20 to 30 nanometer, which is only we can know the size by means of SEM analysis. Next slide, sir. In transmission electron microscope, we know the shape of the nanoparticles. For example, cerium oxide, which is crystalline shape, and this is FeO3, which is in amorphous, which means shapeless. Next slide, sir. So X-ray diffraction. In X-ray diffraction, accurate information regarding the composition, crystalline structure, and crystalline size. So all this are observed from X-ray diffraction method. So next slide, sir. So Fourier transformation. Fourier transformation is used to identify the composition of the nanoparticles. For example, CeO2, which means how much of cerium and how much of oxygen present in the nanofluid. So from that you can identify your how much fluid is efficient. Next slide, sir. So selected area electron diffraction. This is also one of the characterization. So SEAD is a crystallographic experimental technique that can be performed inside a transmission electron microscope. The diffraction from a single crystal in a polycrystalline sample, if the aperture is small enough, when the crystal is large enough. So Fe3O4 nanofluid aperture is small, which means the structure is polycrystalline, shown in the figure. So you can see the dots. So this kind of dots know the structure as polycrystalline. For the perfect crystalline, it shows the ring type. So from the CeO2, it's a perfect crystalline, and Fe3O3 is a polycrystalline structure. It is analyzed only from SEAD, which means selected area diffraction method. And this is done in TEM machine itself, transmission electron microscope machine itself. Next slide, sir. And similar to Fourier transform, another method, energy dispersive spectroscopy. This is also to identify composition of your nanoparticles, which means how much amount of Ce present in the nanoparticles and how much amount of O is present in the nanoparticles. Similarly for Fe3O4, Fe and also oxygen, copper, so carbon, everything will be shown in energy dispersive method. Next is thermal conductivity test. So from the thermal conductivity test, we can identify that your nanofluid is how much amount of heat transfer is possible, because once you know the thermal conductivity, you know the efficiency of your particle. So regarding cerium, it goes up to 0.75, but while going for iron oxide, it goes beyond 1.2, which means the Fe3O4 is best when compared to CeO2 nanofluid. Next slide, sir. So various applications of nanofluids, which is thermal application, fuel additives, lubricants, biomedical, inject printing, surface coating, defense application, electronic cooling, and detergency. Next slide, sir. So the advantages of nanofluid: high specific area, so that you can get more heat transfer, high dispersion, Brownian motion, so reduced particle clogging, because in microchannels, microfluids having clogging, but when you reduce the particle into nano size, it can travel even in microchannel. So then adjustable properties. Next. So before going to thermosiphon, I have to discuss the basic modes of heat transfer. Everyone knows that conduction, convection, and radiation. So all these modes happen in a device which is known as thermosiphon. So next. Yeah, two-phase closed thermosiphon is a highly effective passive device for transmitting a heat at high rates, which was designed by Fegri in 1995. The device which makes use of high heat transfer coefficient available during phase change of working fluid. Next slide, sir. The operation of thermosiphon is sensitive to the working fluid fill volume, which means that you may not fulfill the pipe up to 100%. So that is the main criteria of thermosiphon. So it is experimentally proved that the maximum rate of heat transfer increases with the amount of working fluid for the thermosiphons without wicks. The capillary limit is generally of no concern in the operation of thermosiphons since it's working in a gravity. So that's why I'm saying it's working in a gravity. So there is no capillary limit at all. Next slide, sir. So there are a lot of research gap in this area, container material. So here I am using three kind of materials for my research work. First is copper, and another one is copper. We all of you know that. Then another two materials for my research work is one is 405 stainless steel. The grade of stainless steel I am selected is 405, and one more material is 6063 aluminum. So this is the container material I am selected for my research, and also I am using 5 kinds of nanofluids. One is Fe3O4, and another one is cerium oxide, copper oxide, carbon nanotubes, and also we are using that TiO2 titanium dioxide. Next slide, sir. So thermosiphon, using base fluid, 20% of research work is completed, and using nanofluids, 65% of works going on container material. Only 8% of works is still there. So if anybody wants to do the research work in thermosiphon, my suggestion is to go container materials. You have to select different container for checking the efficiency. Next slide, sir. So this is a thermosiphon, which means we have 3 sections. One is evaporator section, and the mid part is adiabatic section, and the last part is condenser section. So evaporator section is nothing but the heat input we are giving in pipe. Inside the pipe is vacuumized, and fluid is filled up to 30% or 40%. So here I am using nanofluid instead of normal water, so that when the heat input is given, it started to evaporates. So the evaporation goes to condensation. So the heat was given out. Again, it comes back to evaporator section. I already said the problem of nanofluid is settlement. So once your thermosiphon is working in a continuous condition, it will not settle off. But if you are leaving your thermosiphon for 40 days for the Fe3O4 nanofluid, it started to settle, and it may cause some variation in heat transfer. So due to that, the efficiency of the thermosiphon will get affected. Next slide, sir. Applications of thermosiphons, cooling requirements in electronic industries, solar energy. Mainly the thermosiphons are used in solar energy for water heater, air heater, and also waste heat recovery purpose also. The thermosiphons are used. Next slide, sir. And this is my experimental setup. This is my test rig, which is thermosiphon. The heat input given by variac in the condenser section, which is connected to the water tank, and the outlet of the condenser is by leaving to the bucket. The flow rate of condenser section is controlled in rotometer, and the measurement of temperature by means of data acquisition system, and that variac power is noted in wattmeter. Next, sir. Next slide, sir. This is what my pipe size. Evaporator section 250 mm, adiabatic section 250, condenser 250, and this is taken by the help of literature survey. So how you can fix the size of the evaporator section, adiabatic section, and condenser section. We are using 8 thermocouples in various locations. All the thermocouples are K-type thermocouples. Next slide, sir. This is my 6063 aluminum alloy container material. The composition of aluminum is magnesium 0.7, silicon 0.532, Fe 0.35, copper 0.1, magnesium 0.7, Zn 0.02, chromium 0.1, and Al remaining. So remaining is fully aluminum. So this is what the composition of 6063 material. And this is the thermosiphon pipe. This is the heater to give the heat for the evaporator section. And the adiabatic section is insulated with the help of thermowool. And also this is the condenser section. Next, sir. Next slide. So this is the data reduction formula. So we are calculating for thermal resistance, efficiency, and overall heat transfer. Next slide, sir. So this is the advantage of aluminum thermosiphon. The grade I am selecting is 6063 TPCT, which is taken for the experimental procedure as the container material. Aluminum is a silver. All of the know that aluminum is a silvery white material, the 13th element in the periodic table. It is in lightweight, durable, ductile, and malleable. The key qualities make aluminum qualified for engineering applications. Next slide, sir. So here I am using DOE for my experiment. DOE is nothing but design of experiment. So which takes to reduce the number of experiments. For example, if I am doing the same 6063 for DI water, CeO2, and Fe3O4 in a normal experiment, I have to take 27 runs. But while employing DOE, I have cut short of into 17 runs, which means I am taking 17 readings for the experiment. So 10 experiments will cut off while using DOE. So in which I am selecting Box-Benken method. There are a lot of methods. One is composite, central composite method, Box-Benken method, and Plankett-Berman. So the first initiation for this DOE is Plankett-Berman. You are having a lot of input factors. For example, you are having a lot of nanoparticles. Which nanoparticles you have to select for your research? So for that, the Plankett-Berman design will be helpful. And similarly, you are having a lot of factors: heat input, flow rate, inclination angle, similarly size of the nanoparticles. So if you are using Plankett-Berman, it cuts short into few arrives into few input factors. So after once you getting few input factors, you are applying the input factors in the Box-Benken design. Next, sir. So here I am taking my input is heat input, angle of inclination, and flow rate in the condenser section. So the output response, I am taking thermal resistance, efficiency, and overall heat transfer coefficient, which is design of experiment is an efficient procedure for planning the experiments so that the data can be analyzed easily. The experimental tasks start with the selecting of input variables. So that's what I'm saying. For the selecting the input variable itself, you have a Plankett-Berman design, so which is available in DOE software. Then we are going for the output response. Output response also I am taking 3. So 3 cross 3 into 3. So you can have 27 runs if you are taking in the normal way. But if you are using Box-Benken design, you get 17 runs. So that your man work, energy saving, everything will be saved. Next slide, sir. So this is the input parameters I said already, which is run by your design software. So -1, 0, 1. So the first factor I am giving 90, and this is 120, 150. And the angle of inclination I am selecting 30, 60, 90. The flow rate 100, 150, and 200. So these are the run given by our normal strategy, but standard run given by the software is like this. So for that first reading, I am taking for this value only. So because this is your first, so 150, 90, and 150 is my first trial. I am going to take the reading, and the second trial will be in here 120, 60, and 150, which means I am giving the heat input as 120. And angle 60 and flow rate is 150 mm per minute. Next slide, sir. So the effect of thermal resistance on various input parameters of 6063 using a DOE software. Next, sir. So while using DOE software, you usually get ANOVA. So this ANOVA model is significant because I can probability value is less than 001. So what are the values which is less than 001? All the values are significant, and the experimental is 98.80 is correct when compared to the RSM method. Next slide, sir. That's what I'm saying. The model F value is significant. So in this case, AC, BC are significant model. The values are greater than 0.001. So that is the model terms are not significant. The final equation, which is coded factor, is given by the software here, RTH. So this is the equation which is given by the software. Next slide, sir. So this is what the graph we are getting from RSM DOE software. So the surface plot shows heat input, angle, and thermal resistance. Interactive effect of heat input and inclination of thermal resistance. It is found that the increase in heat input, you can see increase in heat input decreases the thermal resistance steeply. We are getting the very minimal value of 0.0064 watts while using Fe3O4 nanofluid. Next slide, sir. This is again second comparing heat input flow rate with the thermal resistance. Next slide, sir. So this is angle, flow rate, and thermal resistance. Next slide, sir. The combined effect of thermal resistance for both the factors from all the heat input parameters, the value of thermal resistance is high at higher inclination angle of 6063 AATPCT. The maximum reduction of thermal resistance can be obtained increasing the heat input and flow rate, which means if you are increasing the heat input to your pipe, your thermal resistance get decreased, which means that the heat transfer of your pipe is more. And similarly, if you are increasing the flow rate, again, you get a good result in thermosiphon. Next, sir. Next slide, sir. Yeah, our experimental result is compared with one more literature result, which means experimental results of Bruce Lee Solomon at 2013. They are using anodized aluminum thermosiphon, size of 350 mm with the inner diameter of 16 mm, tested with heat input range of 50 to 250 watts, achieved a maximum reduction of thermal resistance. Higher input is 250, observed is 0.1 degree watt. In the present study, which means our study, we are using 750 mm and it is tested with heat input the range of 90 to 150 watts. When compared to Bruce Lee Solomon, it was found that reported thermal resistance value is 0.325, but my present work is 0.064. So from the result, it is this may be due to the intensive property of the container material. Hence, can be considered that 6063 AATPCT can be good replacement for the anodized ALTPCT. So that's why I'm saying container material gives the best performance and along with the nanofluids. Next slide, sir. So this is again the mesh graph for DI water, Fe3O4 nanofluid and CO2 nanofluid for the comparison. Next slide, sir. And this is the overall parameters of my research work. So when you're going for RSM optimized value is 0.09 for DI water thermal resistance. Similarly, CO2 you are having 0.11 and for Fe3O4 it is 0.06. The actual reading is also taken and the deviation is very minimal 0.20, 0.66 and 1.5. Similarly, efficiency 52% while using DI water, 49% while using CO2 nanofluid, 56% Fe3O4 nanofluid. And the overall heat transfer coefficient also higher when we are using Fe3O4 nanofluid in 6063 AATPCT. Next slide, sir. So it is seen from the above table that results of RSM model and the experimental values optimization agrees with each other. from the studies, it is identified that Fe3O4 nanofluid is most suitable for 6063 AATPCT. This is due to the presence of folic acid, that is surfactant in Fe3O4 nanofluid, having longer chain of carbon atom. The thermal enhancement between DI water and Fe3O4 nanofluid is 43.3%. Next slide, sir. And finally, I conclude my today's session. Thank you very much for giving me the nice chance, and thanks for the management of SRM Institute of Science and Technology. Thanks for the principal and convener of this program, Dr. G. Prabhakaran sir, and co-convener Dr. V. Tanigevelan sir, and the team members. Thank you very much. Next slide, sir. Yeah, today we have discussed 3 topics: nanofluids, thermosiphon, RSN. If you have any queries?
Participants, if you have any queries, please discuss with us. Participants, if you have any queries or doubts or any clarifications, right now you
Sir,
can
good
discuss.
afternoon, sir.
Yeah, sir.
Sir, which nanofluid can be used as a thermal storage material, sir?
For thermal storage, better you can go for metal side nanoparticles, ma'am, because non-metal side that is not mostly affordable for the thermal storage side. You go for metal particles like Fe3O4, because we have tried Fe3O4, almost we are getting 43.3% of increment in our heat transfer rate.
Okay, sir.
Yeah.
Okay, thank you, sir. Thank you.
Thank you.
Good afternoon, sir.
Thank you, ma'am. Thanks for your query. Anybody else? Anybody else?
Hello.
Yeah.
Yes, please.
Sir, good afternoon, sir. This
Yeah,
is
good afternoon.
Aruna, your former student.
Yeah.
So, what are the container materials? Can you please explain that?
Container materials, we are using brass, copper, aluminum. Aluminum, there are a variety of grades in which I am selecting 6063 as a grade. Even you can go for higher grades, which means 7 series grades are also available. But the thing was, the pipe material is difficult to get it in this particular grade. 7 series grade only is used in aeronautic sessions. Similarly, stainless steel is having also different kinds of grades.
Okay, what is why we are using the container material? Is that any specific reason for that? Because the general material is copper, right? So, if you are using container materials, is that increase the efficiency of the heat pipes? Or?
Yeah, definitely, because copper, if you're only trying with the copper, even my research itself get more than that of copper percentage of improvement in my research work. So while using copper, I'm getting the same Fe3O4 nanofluid gives only 20% of improvement in efficiency. Instead of that, I'm using that Fe3O4 nanofluid and the aluminum container material. I get 43.3%. So that's the difference.
Okay, sir. Thank you.
Thank you.
Anybody else? Participants, anybody else want to have clarifications? Chief guest?
Yeah, sir.
That's over, I think so. So this is the right time to call upon our one of the coordinator, Mr. Krishna, for official vote of thanking of this session.
Hello, sir. Hi, sir.
Yeah, sir.
Thanks for your wonderful session, sir.
Thank you, sir. Thank you.
Okay, sir. Can I go for the formal vote of thanks, sir? Good evening to all present here for this International Faculty Development Program on Futuristic Research in Mechanical Engineering. On behalf of the Department of Mechanical Engineering, Salem Institute of Science and Technology, Ramapuram campus, I'm very glad to have this opportunity to thank you all at this International FDP. First of all, I thank our resource person for this session, Dr. N. Alagappan, for giving an excellent presentation on nanofluids and its application. Thank you, sir. Thank you for the wonderful detailings about that, and the reasons to know there so much of details and applications for particular nanofluid. Thank you very much. And I take the opportunity to thank our honorable chairman, co-chairman, respected director, respected dean, DND, respected vice principal academics, and respected vice principal admin, and our beloved students for giving the opportunity for us to conduct the escaping. Finally, I take the opportunity to thank all the participants from the various colleges to have this session. Thank you, sir. Thank you for it. Thank you.
Thank you very much, sir. Thank you.
Thank you, Professor. In spite of the busy schedule, you accepted and you were given a very nice session. Really thank you.
Thank you, sir. Thank you.
So participants, kindly fill the feedback form for securing your attendance as per the certificates. Ah, ah.